Hey, hi everyone. Going to run through the course notes for week 4, decimals. Now we start over here, decimals and place value. Now we've been here before to this part, units, tens, hundreds, thousands and so on. But now we're going to also look to the other side, to the right side of the decimal place, where we've got tenths, hundreds, thousands and so on. Now notice here, if we do a face place actual like we've got down here, we've got the 0.432 as an example. And let's look at face, place, actual. Let's look at each digit. Well, the face value of the 4 is a 4. We discussed that. We said face value means, like what do you look like? You look like a 4. The place value is what column are you in? We know that's the tenths column, that's the hundredths column, that's the thousandths column. And so that's 4 in the tenths column, and 4 times a tenth. We know 4 times a tenth is the number 4 and 1 times 1 on 10. So it's literally 4 tenths. Okay, and so on. We've got 3 in the hundredths column, worth 3 hundredths, and 2 in the 1,000ths column, which is worth 2 thousandths. Okay, now looking at the trend, well, firstly, I like to think of there's a bit of an axis of symmetry going on, basically around the 1. To the left it's 10, to the right it's tenth. 2 to the left is 100, 2 to the right it's hundredth. You can also just look at the overall trend. We know that we were timesing by 10 in our decimal system to get from one to the next. Well, the same thing's happening, but it's happened from all the way over here. 10 a thousandths is 100. Oops, times 10 I mean. 10 times a hundredth is a tenth, and 10 times a tenth is 1. So this is exactly the same trend as before. We're either timesing by 10 to go left or dividing by 10 to go right. Now, down here we talk about the types of decimals. Just a brief intro at the moment that there's terminating decimals and repeating decimals. Terminating decimals stop, as in we don't need any dots saying that they go on forever. So 0.25, yeah, it stops. But if someone writes 0.2222 dot 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 dot, what they really mean there is it's a repeating decimal. That pattern continues, and mathematically correctly we write it 0.2 with a dot on it. The dot saying, look, that keeps on going forever. Same as 0.3 repeater is 0.3 with a dot. You can also have a line on top. Okay, in Australia it's more the dot, but the line means the same thing. And notice we'll have other examples like 0.121212. That can go on forever. We write that as 0.12 with a dot over both of them, or with a line over both numbers that repeat. But be careful of things like it might be 513535 and the 3 5s keep going. Well, the 0.51, it doesn't get any dots. It's only the 3 5 that gets the dots. And another example, what if it's 0.412412, etc.? Well, we don't put 3 dots. We just put a dot on the first part of the repeating sequence and the last part. I consider them, it's like I'm putting brackets here saying keep repeating all of me. Those dots mean, yeah, repeat everything that's between this and this, inclusive of the end. So that's 412, 412, so on. Should be on the next page as well, some examples. And there it is, we've got a 123, 123, 123. It's either these 2 dots at the ends, or you just give it the line notation. And again, that 4 is not repeating, it's just the 5, 6, 5, 6, 5, 6, so we've got the dots or the line. Now, this thing here in the shaded bit, it's important to look at once, okay? And then we don't need to really go back there. What it's saying is the number 0.251 is, well, you can split it up. It's a 0.2 plus a 0.05 plus a 0.001. I'm just picking on the place values of the columns. We know this is the tenths column, so really that's 2 tenths. We know the 5 is in the hundredths column, so it's plus 5 hundredths. You know the 1 is in the thousandths column. And now if I wanted to add them up, going back to fractions, well, I give them the same denominator. I would want to times the bottom by 100 to make it into 1,000, so I'll times the top by 100 as well. So it becomes 200 on 1000, in other words 1,000. The 5 on 100, let's times top and bottom by 10. And let's leave the last one alone. So now they've all got 3 zeros on the bottom, as in they're all got a denominator of 1,000. If I add them up now, I can call it 251 on 1,000. So look at the little shortcut we've got. All we've got to look at, if 0.251 equals 251 over 1,000, either I can think of the denominator is whatever the last place value is, tenths, hundredths, thousandths, okay? So if it's thousandths, if the last digit's in the thousandths column, overall they're thousandths, or just think there's 3 decimal places. There's going to be 3 zeros. So these 3 decimal places gives me these 3 zeros. It's the same thing. So here when I look at 0.17, well, it's 2 decimal places, so I put over 100, 2 zeros. 251, I put the 251 over, 3 zeros for the 1,000. 1765, yep, I'm going to 3 decimal places here, and hence the 1,000. Simplify it. Note that when you've got a mixed decimal like this, where you've got a whole number part and a decimal part, well, that 1 doesn't have to play part in your conversion to a fraction. It can just sit out the front. Here we separated the 1 and just converted the decimal part. So if I said I've got the number 23.68, it's totally acceptable to say, well, that's 23 plus, well, it's a 0.68, which would be 68 on 100 because of the 2 decimal places. So I've got 23 and 68 hundredths. Sure, I could bring that down, it'd become 34 on 50, then it'd be 17 on 25. I didn't have to make it improper. I could, but I don't know, maybe you just wanted it mixed. So we've got a couple of methods there, and we can see, as it's saying here, a nice shortcut is to notice that the number after the zeros, number of zeros after the 1 in the denominator is equal to the number of decimal places that were in the terminating decimal. That's just saying what I said. The number of decimal places in the terminating decimal was 2. The number of zeros in the denominator was 2. Page down. Let's convert a fraction to a decimal, so going the other way. Now we can use the previous page to go backwards, but we'll come to that on the next page. First I'm going to do a method that always works. There's an issue with the previous method. Now the method that always works is just doing the division. Now I noticed before that we do something here which is about to get introduced in a couple of pages. So let's do it early. What's going to get introduced in a couple of pages is a concept that if I've got some number, 27.1234, if I get that number and times it by 10, times 10 means just move the decimal place 1 space bigger. So that times 10 gives me 271.234. The concept is also, well, what if I times by 100? Well, that'd be move it twice to the right. So now it's 2712.34. Same with divide by 10. That number divide by 10. Well, divide by 10 is the same as times by a tenth. It doesn't matter which you say. It still just makes it smaller by 1 move. It becomes 2.71234. So if we've got that concept that dividing by 100 would be 2 moves smaller, literally 19 on 100 is the number 19 with a decimal point there. Divide by 100, 2 moves smaller. So that was an easy conversion. 19 on 100 is 0.19. What about 3/5? Well, again, I'm saying just do the division. 19 on 100 meant 19 divided by 100. 3 on 5 means 3 divided by 5. So if I get the number 3 and give it some zeros there after a decimal point, that's still 3. Well, divided by 5, how many 5s go into 3? None. If I divide a decimal, that's totally fine, as long as I've got a decimal point there. Note, a point we'll get to soon is that it's not okay for this to be a decimal. That needs to be a whole number, okay? But the one under here, that's okay. If it's got a decimal, so does the answer. So now we're reading how many 3s. I haven't used the 3 yet because I took nothing out of it. So now I'm going to read as a 30. I'm ignoring the decimal point. I'm reading it as a 30. And 5s out of a 30 is 6 with no remainder. So I've stopped. There's the answer. Okay, beautiful. So what you do with these divisions is you just read fractions as top divided by bottom, numerator divided by denominator, and it either terminates, like that did, I got 0 remainder so I stopped, or it keeps going and you see some pattern, you go up, you recognise you've got yourself a terminating decimal. Another one that stops, well, here we said 7 divided by 25, we put the 7 down here. 25s out of a 7 doesn't happen. 25s out of a 70 is 2 with 20 left over, because 2 25s is 50. 25s out of a 200, Well, there's 4 25s in 100, so there's 8 25s in 200 with no remainder. There's my answer. 7 on 25 is 0.28. But then look at delete this one here, 5/6. Okay, it's 5/6. In other words, here's the number 5. I might have to write more zeros. I don't always know with each question how many zeros I need. But 5 divided by 6. 6 is out of a 5 doesn't happen. 6 is out of a 50. Well, 7, 8, 6 is a 48. Best I can do. 6 is out of a 20. I can 3 6s are 18 with 2 left over. And now as soon as I ask myself the same question, I know I'm in some sort of repeating pattern. How many 6s out of a 20? There's 3 with 2 remainder. C, I'm just going to keep writing 3s and writing down 2s as remainders. So that's going to keep going on. So I can say that 5/6 is equal to 0.83. Now I don't write down a few 3s and then put a dot. You put a dot on the first time something repeats. You write in its simplest, most concise form. So that happened there, and then look at what happens with 5/11ths. It's been done as long division there. I'll just do it here as a short division. Here's my 5 divided by 11. 11 out of 5, no. 11 out of 50, well I know 4 11s is 44, that's remainder 6. 11s out of 60, well I know 5 11s is 55, so put a 5 there. 11s out of 50, again, I've already asked myself that question. It was a 4, which was 4 11s is 44, remainder 6. And then 11s into 60 was 5. We're in a pattern. Yep, okay. Decimal point above the decimal point. So my answer to 5/11ths is it's equivalent to, or it's equal to 0.45 dot on 4 and 5. Great. So that method always works. But I was saying, but what about the method before? Well, the method before that we started with is saying, look, it's easy to convert a decimal to a fraction. If I've got a decimal like 0.68, I just call it 68 on 100 because there were 2 decimal places, so there's 2 zeros. So the same goes in reverse. If you've got yourself a fraction where the denominator is some power of 10, it's 10 or 10 squared or 10 cubed, as in 10, 100, 1,000, so on, then yeah, I can easily go backwards. Like if I started with the question, what's 1, 2, 3 on 1,000 converted to a decimal, I'll say, well, it's got 3 zeros, so it'll have 3 decimal places. It'll be 0.123. So yeah, if you can get your decimal to look like what we call a decimal fraction, in other words, the denominator is a 10 or 100 or 1,000 or so on, then life gets easy. On the previous page, we actually did 3 divided by 5 and got 0.6. But I could have said 3/5 times the top by 2 will do, sorry, times the top by 2 and the bottom by 2, because I spotted the denominator can become 10. That's 6 on 10. And we know 6 on 10 is 0.6 because there's 1 0, it means there'll be 1 decimal place. 6/10 is a 6 in the 10th column. Same with 7 on 25. If you spot that multiplying that denominator by 4 will get you to 100, and times by 4 on the top will keep it to be an equivalent fraction, well, I get 28 on 100, which is 0.28. 2 zeros, 2 decimal places. Again here, a denominator of 200 easily became 1,000 by timesing by 5. We did the same to top and bottom. 3 zeros meant 3 decimal places, and there's 0.65 with 3 decimal places. So if you spot that method, great, that can be quick. But not all fractions are going to be able to convert to 100 or 1,000 or so on the bottom. In actual fact, some can convert to that. It's just not going to be easy to see. But anything that cannot convert to that is going to be a repeating decimal. Okay, so we don't have to know whether it will be or won't be. Just if you can't see a way to get the denominator to be 10, 100,000, so on, just do the division. The division will always work. Now the next bit I'll skip because I already talked about that. I need to move that earlier in the notes. Multiplication, division by powers of 10. We did that on the previous page. Now, what's next? Multiplication of decimals. Oh no, sorry. It went too far. Addition and subtraction of decimals. There is really, I'm not going to spend long on this because there's no trick to this apart from align the decimals. It doesn't mean that questions can't be tricky. Like, someone said, what's 0.03 plus 0.007? For instance, you might look at that and think, well, 3 plus 7 is 10, so maybe is it 0.01 or 0.1 or 0.001, something like that. But no, this isn't about a 3 and a 7, and it'll become clear just by lining up the decimal places. If I put the 0.03 there and the 0.007 there, and I can put another 0 there just to make them all line up in columns, I'm not talking about a 3 and a 7 being added. I'm really talking about the analogy of a 30 and a 7 being added. Okay, so just as long as you align the decimals, you really can't go wrong. 0 and 7 is 7, 3 and 0 is 3, 0 and 0 is 0, 0 and 0 is 0, you got the same decimal point. That's addition of decimals. And subtraction of decimals is the same thing. We've got an example here, we're going to do some trading on it. Okay, well that's fine, it still works exactly the same as the decimal, as if the decimal point wasn't there. But the difference is, it is there. Line them up and know that you've got one in the answer. 5 minus 6 is a problem. So here, I've taken the 4 down to a 3, and the 1 I still turns that into a 15. 15 minus 6 is a 9. 3 minus 7 is a problem again, so I'm going to steal from the 2 and give that 1 to here. So I now do 13 minus 7 is 6, and a 1 minus 0 is still 1. Okay, so addition and subtraction of decimals, as long as you line them up, we're all good. Is there an extreme example in that? Maybe 4 minus 0.023, and all I do there is make sure I write the 4 as a decimal with 3 decimal places, just so it matches what I'm actually, let's make it 24, just to show that I'm not just aligning the left, no, I'm aligning the decimal places. Okay, I could put a naught there, but there's no need. Since it's a subtraction, I know I need some noughts on the top to play with. And if I again use the trading method, I look to the left and try and steal from there, but I can't steal from there, so I look to the entire, what's to the left of my 0, and I go, oh, what about that entire 400? Take it back to 399. And where does the 1 go I just stole? Right there. 10 minus 3 is 7, 9 minus 2 is 7, 9 minus 0 is 9, 3 minus 0 is 3, 2 minus nothing is 2. Okay, so there's some examples there. But now multiplication of decimals, that needs a new technique. Let's just bring it down a bit. There we go, and delete a bit. Okay, now it starts off with 0.5 by 5 because we know the answer to that. Because 0.5 is a half. Okay, let's first, I shouldn't assume these things. 0.5 is a half, really? Well, it's got to be a 5 on how many decimal places I've got is how many zeros go on the bottom. 0.5 is literally 5 of the tenths. 5 in the tenths column, and that simplifies down to 1 5 on top to, yeah, 0.5 is a half. So if I'm saying what's 0.5 times 5, I know that a half of 5 is 2.5, so I already know my answer. But let's look at the method, because they're not always going to be that nice. Count the number of decimal places in your question. There's 1 decimal place there. There's no decimal places on 5, it's a whole number. So I've only got 1 decimal place in total in the question. I should have 1 decimal place in the answer. So the technique is, ignore the decimal points, so that just says 5 times 5. My answer is 25, and put your decimal place back in the answer. It's got to be a 2.5. So my question and answer have the same number of decimal places. And again, I knew my answer was 2.5, which is 2.5. So that's good. What about, I'll stick a one that's not there. We're doing extreme one, 0.002 times 0.0013. That'll do. Okay, we've got a few decimal points to play with here. I've got 3 here, and I've got 4 here. So I've got a total number of decimal points of 7. Well, now I ignore the decimal points and just read the question as 2 times 13, which is 26. Don't know if I'm going to fit it. And consider that 26, as weird as it sounds, to be written up against a brick wall. That's just to remind me that I'm not adding zeros to the right of it. That doesn't make any sense. I've got to move to the left of it. My 7 decimal places, well, there's 2 of them. 1, 2, 3, 4, 5, 6, 7. There it is. Yeah, I've got 7 decimal places. 1, 2, 3, 4, 5, 6, 7. And the 2 6 was part of it. Perfect. Right, but the next one here, a 2.2 times a 0.4. one decimal place there, one decimal place there, so 2 in total. Let's ignore the decimal places and it just reads 22 times 4. So 22 times 4 is 88, and I should have 2 decimal places. So there's my answer, and already you can see there's my decimal places. Yeah. The last one here, what'd that have? 3 decimal places and 2, so it's 5 decimal places. There's my answer, and there's my 5 decimal places. Great. Okay. So that's multiplication of decimals. There's no exceptions to those rules. They always work. I did have a question about what if one of them is a whole number. Well, we did one. But I'll just do another one. What if it's 3 times 0.06? Okay, fine. 3 6s are 18. There's part of my answer. Total number of decimal places is, well, there's only 2. So, my answer should have 2. And it's going to be those 2. And an example where it's going to be more like, say, I do 3 times 0.99. It's not particularly nice, but let's do 3 times 0.99 and work it out. Well, I might have to go to the side and work out what's 3 99s. 3 9s is 7, so 27. 3 9s is 27 again, plus the 2 is 29. So there it is at 297. We could have used our mental arithmetic set and said it's the same as 300s minus 3 1s. But anyway, it's 297. But it should only have 2 decimal places, because that's got no decimal places, that's got 2. So it's really 2.97. And you can often make sense of it by going, look, the question was practically 3 times 1. Of course the answer is going to be 3-ish, very close to 3. Great. So there's multiplication of decimals. But what about division of decimals? Unfortunately, it's not the same. Okay, the method just doesn't work. You can see roughly what the answer is going to be. Like as soon as I see, well, let's do one that's nice. As soon as I see a question, 0.016 divided by 0.02, yeah, the answer's got an 8 in it. 16 divided by 2 is 8, but it doesn't work where I just ignore the decimal points, do it, and then put them back. No way. So we need this tactic that is written out here, where we say, write it in fraction form. Technically not a fraction. 0.0016 divided by 0.02. It's not a fraction because fractions have whole numbers on the top and the bottom, not decimals. But it's still mathematically correct. All that means is numerator divided by denominator. I can still say top divided by bottom, even though it's not actually a real life fraction. The other thing I can say is, whatever I do to the bottom of this is okay as long as I do it to the top. Equal treatment. And what I want here is the bottom number to be a whole number. I don't care about the top, we'll see why in a sec, but I do want this 0.02 to become a whole number. And the quickest way to do that would be, can I shift that decimal place twice to the right? And that's achieved by timesing by 100, which is all acceptable if I do it to the top as well. So what do I get after doing that? The bottom has become the number 2 and the top has become 0.16. Now you might see the answer from that, but we can always do a division if the bottom number is whole. We mentioned that before. If I put the bottom number there and 0.16 there, that division is acceptable. We said a decimal here gives you a decimal there in the answer, as long as the number you're dividing by isn't a decimal. Cool. How many 2's can I get out of a naught? I can't get any. 2's out of the number 1? I can't get any. 2's out of the number 16? I can get 8. There's my answer. And note, that's the final answer. It's not like I did something and have to now undo it. What did I do? I wrote it in a different form. That was acceptable. I times top and bottom by 100. Well, that hasn't changed it, because 100 on 100 is just 1. So I changed its form, I times it by 1, and I found the answer to that. So that is the precise answer. Look at the first example here. 25.5 divided by 0.3, wrote it like a fraction. Times 10 and times 10 actually made top and bottom whole. I only cared about the bottom, but it happened to make both whole. And 255 divided by 3 is 85. Now that might look odd. How can a decimal question give you this nice whole number? Well, that'll happen. I mean, that's a big number divided by a little number. That was saying how many of these little 0.3s can you get out of a 25.5? And I know it's quite a few, and it may be a whole number, and it was. Let's confirm that. If I can get 85 of these little things out of that, that means that 85 times that little thing should return me to 25.5. Well, if I went to the side and said, what is 3 85s, I'd get an answer of 255. If I looked at how many decimal places in the question, it's only one. So my answer is going to be 25.5, which is exactly what we had. So that's all working. The next example is one where we didn't lose the denominator of the decimal, off the top. 0.056 divided by 0.04, we wrote it as a fraction. We said, I could have times top and bottom by 1,000, but it actually makes more work. If I times top and bottom by 1,000, I would have gotten a 56 on a 40. My question to you is, would you rather divide by 4 or 40? I'd rather divide by 4. So I'm just going to leave the denominator whole. I'm not going to try and make the numerator whole. Just doesn't matter. So 2 moves made the denominator 4, 2 moves made the numerator 5.6, and then went 4s into 5 goes once with 1 left over, 4s into 16 goes 4. My answer was 1.4. Okay, and another one here. So decimal division hopefully makes sense. Now rounding of decimals, well, let's look at this example here. We've probably all rounded decimals before. We've got 2 ways of rounding numbers. First one's decimal places, the next one on the next page is significant figures. Significant figures is more useful because it doesn't have to be a decimal to be able to use that sort of rounding. We'll see it in a sec. But decimal places, it does have to be a decimal. The example there is 2.4538. And the first question asks, what's that to the nearest 3 decimal places? Or it could ask the nearest thousandth. There's nothing different in those 2 questions because the first decimal place is the tenths column, the second is the hundredths, and the third is the thousandths. So it's the same question. We normally say decimal places, but we could just as equally use this other term. It's just our place value headings. So 3 decimal places means, okay, 1, 2, 3. I'm going to stop there. But there's always a decision before I finish, and that is, should I round this 3 up or leave it alone? And the reason for that is, look at the number, 2.4538. If I'm making a decision between, should I call it 2.453, or should I round it up to 2.454? The answer is, well, which is it closest to? And it's closer to 4 because of that 8. Okay? Consider it on here, it's only 2 steps to that, and it's 8 steps down to that. So our decision is, as it says here, I put a line there anyway in my method. I then make a decision. If I'm followed by a 5 or greater, I will round up. If I'm followed by less than 5, I will leave it alone. And that has it rounding to the closer number. With the exception, if it was a 5 after it, well, I'm not really rounding to the closer number necessarily. It's just halfway. If I ask the question, what should I do with 2.35? And we said, well, is it closer to 2.4 or is it closer to 2.3? The answer is it's just as close to both. It's 0.05 away from both. So it's slap bang in the middle. It's not closer to either. But a decision's been made just for consistency. If it's on the halfway mark, if it's 5 or more, round up. So I would round 2.35 up to 2.4. Okay? Halfway mark is 5, take it up. Note also, if someone asks me to round 2.4538 to 1 decimal place, I don't round it to 3 and then 2 and then 1. You can get errors where that digit keeps changing. No, you only ever want to round an entire number. Like someone says to me, look, here's a number, 1.25847, whatever's going on. That might be the output from the calculator screen. And they say, give me that to 2 decimal places. I don't work my way up or down to 2 decimal places by taking each digit at a time. I just go for it. 2 decimal places means I look after my second decimal place and make a decision. Will it be 1.25 or will it be 1.26? And since again it's 5 or greater, I'm going up. The answer to that 1 to 2 decimal places is 1.26 rounded to 2 dp. Perfect. So that's decimal places, and clearly I needed decimal places to be able to round decimal places. If someone asks me to round this number, hey look, this bank made a profit of $2412138, the best I can do to that is round it to 0 decimal places, which it already is. It's got no decimal places. So if I want to round that number, if we don't really care about the $138 the bank made, we need to be able to round bigger numbers, okay, whole numbers, and that's what the next page is for. Significant figures, you can round large numbers, okay, whole numbers can be rounded. Firstly, we start off with decimals anyway, because it can be used for both. The first question or first example talks about 0.315419848 and goes through the steps of how do we round that to 3 significant figures. Now the first rule of significant figures is you don't start counting significant figures until you hit your first non-zero. As in, there's no reason why I would do it, but I could put noughts here. I know I've got naught units. I could put a naught for naught tens, a naught for naught hundred, thousand, so on, you know. That'd be irrelevant, but I clearly don't want to start counting the noughts. I'm going to start counting my significant figures right here. 3 is my first non-zero. It's my first significant figure. I can consider the other zeros as placeholders, stuff like that, that just telling me there's none of this column. My second and third significant figures are here. So now I've got a decision. My only decision is, do I round that 5 up or down? It's only followed by a 4, so leave it alone. That, rounded 3 significant figures, is 0.315. You might say, but hang on, that's 4 figures. 0 is a figure. Yeah, it is. 3 significant figures doesn't mean you're only going to write down 3 figures. It means 3 of them are significant. That 0 is just there because by convention, we don't just write 0.315, we write 0 point. Probably just because the dot can be hard to see at times, but it's just a convention. Technically it's not wrong to write 0.315, but I won't be doing it. 0.315. So that's what these instructions are saying. But let's look at these instructions on the next number, which is 9,815,439. If I want 3 significant figures here, again I could have a stack of zeros if I wanted. I start counting at the first non-zero, which is clearly the 9. 1, 2, 3. Now I'll put a line there and make a decision on that last digit. Leave it alone or take it up. And I'm going to take it up because we said 5 or above, take it up. So I'm not going to stop at 981, I'm going to call it 982. That's 3 significant figures, but the bank's profit of $9,815,439 is very different to $982. Don't just leave it like that. We need 1, 2, 3, 4 zeros after it. Because that 9 should still be in the millions column. I needed those zeros. I'm not calling them significant figures because the 9 and 82 were the significant ones I kept. But you've got to put the zeros back. If I'm ignoring 4 digits, you've got to put them back as zeros. So would you agree that the bank's profit was about 9,820,000? Yeah. And it's closer to 9,820,000 than it was to 9,810,000. So there's our rules for significant figures. Something else I'll check here is what if the number, what if the number was 0.003000527? What if that got, I was asked to report that to 3 significant figures? Well, I said we start counting significant figures at the first non-zero, which yoink is that. But once we start counting figures, you don't stop. Just because that's a 0 doesn't mean it's not significant. It's not just a placeholder, it's as valid as any other digit. So once you start counting, don't stop. There's my first 3 significant figures. Then I put a line there and say, well, do I leave it alone at 0.00300, or do I round up to 0.00301? And 5 on the halfway mark says, up you go. So my final answer here is 0.00301. That is 3 significant figures. Okay? So once you start counting, keep going. There's some examples there. I don't know if they do anything we didn't just do. Again, I'm not rounding and then rounding the round and then rounding the round. I'm going back to the original number. Okay? Just 3 significant figures was, okay, 2.75 followed by a 2, so leave it alone. 2 significant figures. 2.7 are my first 2 significant figures followed by a 5, so do take it up to 2.8. And 1 significant figure, well, that's only going to be one number. I've got to represent this with one number. So I put my line here. And I say, well, what's it followed by? It's followed by 7, so I round up. So yeah, it's a 3. And here is 3, 5, 2, 8, 4 to 3 significant figures. There's my 3 significant figures, but round up because it's an 8 and put in 2 more. Don't just leave the 8, 4 away. Put 2 zeros there. And so on. 2 significant figures. Well, no rounding needed because of the 2. And I better put 3 zeros there. And to 1 significant figure, I will round up because the 3 is followed by a 5, so the 3 goes up to a 4, and I've got 1, 2, 3, 4 zeros to put with it. They're all approximations of varying accuracy for the number 35,284. Now, significant figures in the real world. Let you read through that, but I will say that's more background. That's more talking about, well, you know, what factors determine the number of significant figures I can write. If I'm using an old dodgy metal ruler, measuring tape, I forget if there's a proper name for them. I just call them measuring tape, you know, and they spiral up inside. Well, I can't be too accurate on it. I'm not going to use that tape and say, look, that table is 2.1385 meters long. I'm probably kidding myself to even say it's 2.14 meters long because, you know, it's very inaccurate. So there is a real life application to this, and if you go into the sciences, you know, there'll be discussions on that. But that's just an introduction to say, look, you know, how accurate can we get? Depends on the instrument and the size of the object being measured. Good luck using my tape measure to measure the width of a flea. Anyway, but what matters to us, back to maths, is determination of the number of significant figures. So, how many figures are significant if we get quoted a number? Let's go straight to here. All non-zero numbers are significant. So if you've got a number like 36.41, I'm not going to dispute any of them. They're all valid. The truth is, I mean, that's 4 significant figures. 36.41 grams is correct to 4 significant figures, with a bit of a hesitance there. Truth is that last digit 1, we could have rounded up to 1, or we might have rounded down to 1. I don't really know. We call the 4 numbers significant because we say they've all been measured. But the last digit, yeah, maybe it was 36 point, I'll just make an example, 0.41432. Maybe it was measured with some super instrument that told me that. And I go, look, we're kidding ourselves. It's not really that accurate. Let's just report it to 4 significant figures. Well, I'd put a line there, and I would not round the 1 up because it's followed by 4. I'd leave it alone. So you can say, look, that 1, maybe it was higher than that. Yeah, maybe it was. Maybe it was lower than it got rounded up. But anyway, this is 4 significant figures. What about the next one? All zeros between non-zero numbers are significant. Well, that's what I said before. When you start counting significant figures, just because you hit a 0, don't stop. My first significant figure is a 4. And then the second is a 0, the third is a 1, the fourth is a 0, and the fifth is a 6. They are all significant figures. They all count. They're all actually measured. Okay. Zeros appearing as the first figures in a number are not significant. We've already said that too. You don't start counting significant figures until you've hit the first non-zero. So you scoot along until you hit a non-zero. 3, 5, that's only 2 significant figures. That 0 is just a placeholder. All zeros to the right of a decimal point and to the right of non-zero numbers are significant. Okay, now this could seem weird at first, because we will have said in the past that the number 5, the number 5.0, and the number 5.00, they're all just the number 5, and mathematically they are. But let's talk significant figures for a moment. If someone said, this thing is 5 kilometers away, this shop, I'm pretty confident it's not exactly 5 kilometers. I reckon maybe it's 4.5 and they round it up, or 5.4 and they round it down. 5 kilometers is pretty rough. But if someone tells me it's 5.0 kilometers, that statement of 0.0 tells me, no, it's been measured. It might have been 5.04 and it got rounded down. It might have been 4.96 and it got rounded up. But that is significant. That's telling us, no, we measured it fairly accurately. And 5.00, well, that's even more accurate. Okay? that's saying, well, let's convert kilometres to metres for a sec. If I converted that, 5 kilometres is 5,000 metres, and really it's saying if you gave me 3 significant figures, it's saying all those 3 are significant. So I'm saying I'm a bit iffy about that last. There's only 10 metres in in error there, but I've measured it accurately. Same. Well, okay, here's an ambiguous one. I ask someone where the bookshop is, and they say, oh, it's 600 metres away. I don't actually know what they mean by that. Do you mean it's like 550 and you round it up? Or were those zeros accurate? Did you actually measure it and it's 600? So sometimes you don't know how accurate a number is. If someone tells me it's 600 metres away to one significant figure, I go, okay, it's rough. It might be 550, it might be 649. Yeah, okay. But if someone tells me it's 600 metres to 3 significant figures, that's a big difference to me. That means, yes, you measured it down to the nearest metre. Okay, so if there's zeros on the end of a whole number, I really don't know unless you tell me. But if there's zeros on the end of a decimal, someone tells me something is 0.600 microns measured on a microscope, well, these two are accurate. They're deliberately put there to say, I measured this and it was 0, I measured this and it was 0. So that is 3 significant figures. So that last point, all zeros to the right of a decimal point and to the right of non-zero numbers are significant. So that's, I don't count that 0, but I count 1, 2, 3 significant, and 11.0, 1, 2, 3 significant. Alright, well that's the exercise. Let's look at the exercises. That's the lecture. Why aren't you page downing for me? Let's look. So face, place, actual. Well, we've just got to know that to the right of the decimal point is tenth, then hundredth, then thousandth, and so on in the places. Converting from decimal to fraction. Well, they're nice because every single decimal like that one, 0.625, I know how to convert that instantly to a fraction. It's got 3 decimal places, so it's got 3 zeros on the bottom. I shouldn't have written the 0 point. We write the digits from the decimal, 65, over the 1,000. And sure, it says reduced to its lowest form. You might spot they have a common factor of 5. You might spot they've got a common factor of 25. Less likely, you might spot there's a common factor of 125. But whatever you spot, I'll just do 25. There's 4 25s in 100, so there'll be 40 25s in 1,000. There's 4 25s in 100, so there's 6 4s, it's 24 plus 1. So there's 25 25s in there. 25 and 40, I've got 5 5s there and 8 5s there. Okay, it came down to 5 8, so we've still got a bit of work maybe simplifying, but the actual conversion to fraction from a decimal is pretty easy. Notice that in our course we aren't going to convert like 0.45 repeater. That can be converted to a fraction. I'll tell you now, it's 45 on 99. That's right, isn't it? I don't want that in the video going on forever. Yeah, it is. I knew that. But we're not going to do them. We're not going to be requested to turn that into a fraction. Okay? So you'll note that all we've said is terminating decimals. We might have to go from a fraction to a terminating decimal, but that's not too hard because that just comes from division. Either I get a terminating answer or I don't. Like here, 2/9. Well, maybe when I do my division, it'll end up terminating, maybe it'll end up recurring. I know it's going to recur. Here's my 2, and it'll pop its head out pretty quickly. How many 9s can I get out of a 2? None. 9s out of a 20, well 2 9s are 18, remainder 2. 9s out of a 20, 2 9s are 18, remainder 2. Blah blah blah, on the pattern. You can already see 2 9s is 0.2 repeater. So that's how all those fraction to decimals, some of them you might see as an easier way, like 4/5, you might call it 8/10, and you might call it 0.8. If you can see a way to do it by making the denominator 10 or 100 or so on, yep. And with the 3 and 5/12, the 3 doesn't have to take part in it, the 3 can sit out the front while you convert the 5/12. We've also got addition, subtraction, as long as you line the decimals you're right. Multiplication was when we ignored the decimal places, or the decimal points, did the question, and then put back the number of decimal places. That was pretty nice. And the division was when we made them look like fractions. Made the denominator a whole number. And then we've got some rounding ones. Great, I hope this was useful, and we'll talk again. Alright, see ya.